Hello everyone, I am just today to present a video on assignment 1 oral basics. So the figure here shows the oral pipeline which consists of the environment, learning agent, actions, rewards, punishment and observations. So basically an oral agent can sense its environment and choose actions to perform in the environment. And the environment is a physical component and the world where the agent lives in and operates. So, and the action is the movement or the other type of decisions available to the agent. And executed action will affect the environment. An action may have a long-term consequences. And observation is the information gathered by the agent from the state of the environment. And state is the snapshot of the environment at a particular point in a time. Reward is a feedback signal. So, using this oral pipeline, we implement this assignment. And we use OpenAI Gym and GitHub to explore the concept mentioned in this assignment. Firstly, we install Gymnasium using the pip install -q Gymnasium, and we import Gymnasium as Gym. And Gym contains many environments, but basically we explore here only two classic control environments. They are the cardboard environment and the mountain car environment. Cardboard environment is attached to a car that moves along the track. So the goal here is to balance the pole by applying the force to the car. That means we need to apply appropriate force that can balance the pole and the mountain car. The mountain car here is we need to give the minimum momentum so that the car moves to the yellow flag, which is the goal of this mountain car. So let me explain detail about this mountain car and cart pole. Coming to mountain car, it has three action spaces which are discrete and observation space of two. And mountain car has spaces two, which are there. They are 0 and 1. 0 represents position of the car along the x-axis. These are the minimum and maximum. And 1 represents the velocity of the car. So there are three action spaces as said earlier. There 0, 1, 2. 0 represent the car is accelerated towards the left, and 1 represents the car is not accelerating, and 2 represented the car is accelerating to the right. And this is the formula for the transition dynamic and the reward. The goal is to reach the flat top of the right hill as quickly as possible. So for the every time step, we give a reward for the penalized step. It has -1. And these are the starting state and the episode end. These are the few details about the mountain car. And when coming to cart pole has two action spaces and observation shape of 4, and so 0 action space represents push cart to the left and 1 represents push cart to the right. These are the action observation space. They are 0, 1, 2, 3, which represents 0 represents cart position, 1 represent cart velocity, 2 represent pole angle, 3 represent pole angular velocity. And we give reward as +1 for every step taken, including the termination step. And this is the starting state of the uniformly random assigned state. These are the some few details about the cart pole. So initially we create the environment using the command gym.make for the both mountain car and the cart pole. So after creating the environment, we reset the environment to get started using the command mountain car environment dot reset cart pole environment dot reset. And we and we print the number of action spaces for each in the mountain car and the cart pole. So now we take a sample, a random action from the action space of mountain car, and by sending the dart sample, and we take a step in the mountain car with the random action above. So, and we print random action, observation, reward, termination, and truncated. So the input action is two. As mentioned here, if the as mentioned here, if the input action is two, then it is accelerating towards right. So, and the observation here is it is providing here the velocity, the position of the car along the x-axis and velocity of the car. And as it is not successful to reach the yellow flag, it is penalized with -1, and it is not yet terminated because it is not reached to the uh, flag, and it is not truncated because it is not reached the maximum attempt of 200 episodes. Uh, this is the explanation of these attributes. And now we perform these action sequences for the cart pole. So we take 5 forward actions and 5 backward actions. We define the action sequence as 1 1 1 1 0 0 0 0. So we use the statement, we initialize terminate equal to false, and we just while statement while terminate not equal to true. Then we perform this for loop and print the these input action, output observation, output reward, output terminated, output truncated for all the 5 forward actions, one for all the 5 backward actions. So this is the input action one, and the output observation. For the cart pole, there are 4 observation spaces. So we are getting 4, which are cart position, cart velocity, pole angle, pole angular velocity. And we penalized with the reward 1, and it's not terminated, so it's false, and it's not truncated, so it is false. So it is done for the 5 forward actions and 5 backward actions. And now let us reset the cart pole environment, and we'll output the initial observations and output the bound limit for the observation space. So we use the command cart initial cart pole environment dot reset and environment cart reset to reset the environment, and we print the cart pole observation and shape. And the observation shape has a limit on how high and low the values are, as described in this gymnasium and cart pole window. So these are the outputs for the maximum and minimum observation limits. And now we perform some of the things on Acrobat environment. So Acrobat environment is also a classic control environment in the gymnasium. So it has a 3 discrete action spaces and 6 observation shapes. So 0 represents apply -1 torque to the actual joint. Basically, these Acrobat is joint between the link is, and the goal is to apply torque on the equator joint to swing a free end of the linear chain above a given height while starting from the initial state of the angling downwards. And these are the observation space and action space of the Acrobat. Now coming to the code. Now coming to the Acrobat environment, we make the environment using the gym.make, and we print the number of actions spaces in the environment, and we reset the environment here, and we print the observation space, and then we take the sample environment and take the step in the environment, and we print the reward for the environment. So these are the outputs. The number of actions in the action space is 3, and the initial observations are given this as there are 6. and the maximum minimum limits of that acrobat observations are given here, and it is penalized with the reward one. Now, since the oral agent goal is to maximize the cumulative work, the reward is only feedback signal. So we plot a learning curve. So the learning curve indicates the uh, accurate performance of the algorithm. An upward trending learning curve indicates that the agent is learning to perform the task effectively. So we plot the learning curve in this here. So for this, we install stable baseline 3 and PPO. Uh, PPO is a reinforced algorithm which is useful in the implementing the AI projects. We install dash and stable baseline 3 using the commands. Then after that, we import OS and we import NumPy as MP, and we import gym, and we import discrete using the gym dot spaces dot discrete. So, and we import MLP policy from the stable baseline 3, and we import evaluation policies from the stable baseline 3 to plot this graph. So, and we write this command import warnings. If we get some warnings, we can ignore them, and we import load results, TS2X5 plot results, base callback, monitor from stable baseline 3. And basically to plot the graph, we use pandas, and we import them as PD and matplotlib dot as PLT. So to create again the environment using the gym.make, and we there are two discrete spaces here, and we create a log directory using the temp, and we make directory here. Creating the environment wrapper, that is monitor. We create an environmental wrapper which monitors the card pool and the log directory, and we use multi-layer perceptrons for policies as discussed above. So we use the PPO with the argument attributes MLP policy card pool and one monitor and verbose 0. So we train here for 20,000 time steps for card pool, so that we use a callback function to record the reward. So we use a class reward callback, and here with the method init function with the self. Self is used to access these arguments in the other method or the class. So we use the argument check frequency, int, log directory, verbose, string, int, and all this. And we assign self dot check frequency and log directory to access them in other methods. So we check for self dot 10 calls modulo division self dot check frequency equal to 10. We retrieve the training reward and assign it to x comma y. So if the length of the x is greater than 0, then we do the uh, mean reward and check the frequency. So if self dot verbose is greater than equal to 1, we print a number of time steps and mean reward for the last self check frequency episodes. So that is the function callback function to record the reward. And instantiate callback, reward callback is used for every user to check every 200 episodes. So we train the card pool and we check for the reward callback. So here we train the card pool and check the reward for the every time steps of the 200, and we have calculated the mean reward for the last 200 episodes. So the output shows here for every 200 rewards, the mean reward has been calculated. For every 200 episodes, the mean reward has been calculated. And so We use MATLAB to plot the reward that was obtained during the training. And so fetch the data, we need to fetch the data to plot, and we need to skip the first two rows uh, and select just rewards. We are skipping the first two rows 0, 1 and plotting for the others. And we use fig ax for plotting the graph, and x is x is the length of the reward data, and we plot length of the reward data here. So and yeah, we given a title reward collected over time steps, and we labeled x-axis as episode and y-axis as reward per episode, and this is the graph that we update. Now we can also evaluate an agent by examining the reward average reward over a certain number of episode, for example 100 or 200. So we evaluate the reward for 100 episodes, and we print the main reward for the 100 episode for trained policy in the card pool, which is as 500. Now we install dependencies to record the environmental render. So these are the dependencies we install to record the environment. So for the video recording, we import recorder from collab gym render.recorder, and we use these code for recording the video. We use the record environment f videos observation record environment.reset, and the video length, and we give these variables and attributes to record the video. And finally we render the video using the video render command for the card pool and agent of the card pool, and we record the video, and that it is obtained here. Here you can see there that the force is applied to balance the pole on the to balance the pole. The video shows here, and this is the output of this card pole to balance the pole. Thank you.